Okay, I had to start that one over because we had a little incident down here. We will not describe. I'm talking to Berkeley. He's my audience now here. Okay, so let me think where we stopped. We were talking about, okay, I know where we're at. So we learned that as frequency increases, energy increases, but we also learned that as wavelength, this is very confusing. Don't smile at me, Berkeley. You're going to make me not be able to concentrate. We know that as wavelength gets smaller, frequency gets larger. So that would also tell us that the energy is going to increase as the wavelength gets smaller. And if you look at that chart again on page 105, you can see that gamma rays are really, really small. They're at 10 to the negative 12th meter. And now the dog is sitting on Berkeley's lap. I'm super distracted. 10 super small wavelength, high energy, high frequency. And as waves get really big, like 10 to the second meters, which is radio waves, we have big wavelength, we have low frequency, low energy. So that's why gamma rays are dangerous, lots of energy, and radio waves are not. But some would say that radio waves are bad for you too. But hey, Delaney, I'll talk to you in just a minute. I just have to finish my video here. I'm doing a video for school that I've already started over. So, okay, I love you. Did you have a good day at work? Okay, good. Some people would argue that radio waves are dangerous, even though they're lower energy, but the jury's still out on that. So it's not a for sure. That's just a theory. Okay, so we get from, let's see, do they tell us how we get this? I don't remember. Let's see, they talk about the relationship between frequency and energy, which we just talked about. And then we also learn, yeah, they don't tell you what. Physics, I think you learn more why you have these equations. They just tell us about this equation that energy is equal to H. I'm always like, what is H? Energy is equal to, hey, don't interrupt me. This is the beauty of making a video. Oh, Lord, I wish you guys could see, but I can't turn the camera around. Here, we'll have one short interruption. Berkeley with Beatrice. This is what I'm trying to look at while I'm giving this video. So now you'll know I'm distracted. Okay, so we learned that energy equals Planck's constant. So if you watch Stranger Things, you'll know why I enjoyed that and why the theme to the Neverending Story was going through my head as I was studying this. Okay, energy equals Planck's constant times frequency. Planck's constant is named after the German physicist Max Planck. And so it just relates energy and frequency. And it's just a constant. And I will get this to you. Nobody on Stranger Things knew it except for the really smart Russian scientist. So, no, he even had it wrong. No, it was a really smart little girl from I can't remember the name of the camp. Delaney will kill me. Okay, let's get focused here. 6.63 times 10 to the negative 34th. And it's joules per hertz. Okay, here's some of those great physics derived units, joules per hertz. Okay, so if we know that Planck's constant, that's H, is in joules per hertz, let's look at that. Joules per hertz times frequency. What is frequency? It's that nothing per hertz, 1 per hertz, right? Or, no, 1 per second, also known as hertz. So, no, let's call it hertz, I'm sorry. We'll do that later. Hertz is 1 per second, and we're going to just multiply it times hertz. Okay, so I'm multiplying the units. Okay, so energy, so I can tell you so you can learn what the units of energy are. Planck's constant is joules per hertz. Frequency is hertz. So what happens when we multiply those, cancel out, and we're left with energy is equal to joules. So joules, Joules, you'll encounter this in physics. But we might as well visit it now. Joules are a unit of measurement for energy. And if we put, what do they do next? Energy is equal to joules. Joules per hertz. Why do we do joules per hertz? You can also, no, can you get the dog out of here? I cannot concentrate for the life of me with this dog rolling around here. Joules per hertz, that was Planck's constant, okay? There's Planck's. How do you spell Planck's? It's different than the original language. Okay. We can also say that in terms of 1 per second, what I started to do earlier. I can say joules per 1 per second. I'm just plugging that in for hertz. I'm just going back to Planck's constant. And then this is the same as joules times remember when I take something to the top, I invert it. So now I have just, instead of 1 over s, I have s over 1, which is the same as s. And this is like joules times seconds. So they're joule seconds. So Hertz, or excuse me, Planck's constant is in joule seconds, you could also call it. So you could call it the joules per Hertz or joule seconds. These are just, I kind of want you to see this because this is an introduction to physics and why this is my primary motivation when I'm talking to you about units and unit conversions, why you have to understand it. Because when you get to physics, you get to these very complicated unit conversions, and they sometimes give you the like final unit that you need, but they also help you to know if you put things in the right place because things should cancel out and be what you expect them to be. When you get to energy, it should come out as joules. If it doesn't come out as joules, you like if it's joules per second or I don't know, whatever, you did something wrong. And those units can be helpful too. So that's my primary motivation in taking you through that. Sit down and write that down. It's one thing to watch me do it. Actually write those units out and try it yourself to make sure it makes sense. Okay, hang with me, guys. Last thing that we're going to talk about is the Bohr model of the atom. But there's a lot of information here, okay? You've got to be making sure you're reading this. You can't just go by my videos, which are like less than stellar in my knowledge of it. The book is much better. What did you say, Berkeley? No comment. They do have this little section on, which is just interesting and a good, like, all glory to God kind of thing about creation, talking about how the eye detects color between rods and cones and how different rods are for, rods are not, they're for like gray, like gray tones, black and white tones, and cones detect color, and they detect that based, if someone is talking to me from upstairs, you absolutely just need to go to bed unless your arm is like broken or you're throwing up. Do you understand? No. Oh, I thought you were one of the kids. I'm sorry. They will not go to bed tonight. Okay, sorry, I'm almost done. So it has to do with how much energy comes from that wavelength of that color. The cones in your eye are designed to pick up those specific energy levels, and then they send the message to the brain. Super interesting, and I think really enough. If you read it, it is super interesting.
Are you still making a video?
I am making a video. No sarcasm.
I can hear all of this?
Huh? Yes, they can hear all of this.
Hi.
Well, it's Abby. It's Abby and Caitlin and Abby Nix and Jonathan. So
Hi,
and Emily.
guys.
So Delaney says hi. Okay,
I'm
so
sure they can hear me.
yeah, I'm sure they can hear you.
Wait, I thought they were taking chemistry.
Guys, let me just finish this video. They are taking chemistry. This is chemistry.
Chemistry is the best subject.
Okay, Berkeley asks, why are we teaching physics? Because all this physics is going to come around to understand the Bohr model of the atom, and I'm trying to remember why.
We're going to use it again.
I've been
Be quiet,
chemistry
stop.
For a month and I haven't gotten physics.
Silence or leave the room. Okay, so if you read the chapter, there's a really great discussion about how Bohr developed his model, and it has to do with using the light that was emitted from elements when electricity was passed through it. So if electricity was passed through something, shh, be quiet. Take your coughing self out of the room. We're on our final moment here. When you pass electricity through something, you heat it up. So that's why if you get electrocuted, it burns the inside of your body. It's bad to get electrocuted. Heat comes from that. So the other interesting thing is that each element emits its own unique set of wavelengths when it's heated or electrified. So that's how scientists can determine the elemental makeup of stars. They can look, so when you look at a star, it looks like all white light, but they can look at that and see all the individual colors of light and see which elements are emitting those colors. And that it's like are you guys laughing at me?
No, I'm laughing at this Lisa that just texted me.
Ah, okay. Can only imagine. That's also on the video, so just so you know. Those wavelengths, those elements give off a specific combination of wavelengths, and so they can see what elements are in those stars, and it's called spectrometry. Did I say that right? Using a spectrometer. That's also how you can determine, that's chemists' primary way of determining what different substances they have. Analyzing an unknown substance, it can use a spectrometer because they can look at the different wavelengths that are emitted from that using a spectrometer. So pretty cool stuff. Way more interesting in the book. So Bohr used this information to develop his model of the atom, as he suggested that electrons might have several possible orbits around the nucleus instead of just a circle, like Rutherford proposed. So Rutherford just said they're moving, and they're moving in a circle. That's where he left off. And then Bohr said, sure, they're moving, but they are possibly moving in different orbits, not just one, and they might be able to jump from one orbit to another. The light is coming back, I promise. Why we studied all this stuff about light. You'll have to study it again later anyway, so at least you've heard it once before. And neutrons were also discovered around this time, but it's a little less relevant to our conversation. So he discovered electrons. Basically, he did math that made him, it's hard to, I'm trying to get the chicken and egg thing here. He did all this math that helped him theorize that this could happen. And he didn't actually know why it might be happening, but it fit his model. So this is an assumption that he had to go on. So he discovered electrons could jump from one orbit to another, but never in between. And this was called a quantum assumption. I don't know why it's called a quantum assumption. I can't tell you that, but it is called a quantum assumption. And he had to make this assumption for his model, even though he didn't entirely know why it might be. But here's the important part to you. And if an electron wants to jump, so if it's close to the nucleus and it wants to jump farther away from the nucleus, it needs energy. It needs energy to get away from that nucleus. And so it has to get that energy from heat or primarily from electricity. Not always from electricity. It could be from combustion, as we'll learn about later. So think about it. Is it starting to make you think of anything? And when it wants to go, if it's far away from the nucleus and it wants to get closer, so we're just talking about light and electrifying those elements. Hopefully it's making you think of something. Probably not, because I'm not explaining it very well. If those electrons want to get closer to the nucleus, they have to give off some energy. And they give off that energy usually in the form of light. So they emit light when they are jumping far away from the nucleus to get closer to the nucleus. So when that electron is taking on energy and moving away from the nucleus, we say it's excited. And when it's moving far away from the nucleus, closer to getting rid of energy, it's de-excited. Those words make sense with what's happening. And so it emits energy. So basically what that's telling us, I feel like there's this big, that's so cool, aha moment, but I'm not bringing it there very well. If energy is given off, thanks Sully, if energy is given off, an electron is moving, light is emitted. So when we are seeing that light emitted from a gas that's being heated, that's from electrons de-exciting. They're moving back towards the nucleus. And so I feel like you guys are laughing at me. You're going to have to take yourselves somewhere else. So when we look at fire, that's why we see the flames of a fire. I thought that was really cool. I've always wondered, what the heck are the flames of fire? Where does that come from? So heat is produced in combustion. So we have combustion. It's kind of chemical change. Combustion is happening. The wood is burning. It gives off different gases. And as the combustion excites the electrons in the gases around the fire from the heat, so combustion gives off heat, that heat is exciting those electrons. They're moving away. They get excited. They take on energy. They move away from the nucleus. But as you'll read in the book, they do that, but as they sit there, they don't really want to be far away. They want to get closer. So they will de-excite, and as they de-excite, they give off energy in the form of light. And that light is what the fire is. That's what you see when they de-excite. So I think it's actually pretty interesting. Hopefully you think so too. My children will probably roll their eyes at me right now. So his math...
Thanks for giving me so much.
I know, because you guys were being sarcastic before. Okay, let me just finish. So the math that he did determine... Guys, be quiet. His math that he did determine the energy of each electron orbit and how much energy it took to jump from one orbit to another. And that told him the wavelength of light that electrons must emit to de-excite, because we know that wavelength is related to energy, right? If we have a really small wavelength, we have high energy. So that math is beyond me. That math is beyond you. But if you take chemistry, high-level chemistry in college, you will do that. So what we're going to learn about in the next set of videos for a different day is there is another theory to atomic structure, which is the quantum mechanical model. Is going to be a whole load of information. Delaney can attest to that, right? All those orbitals and S and P and D and F. Do you remember that? And only 2 per S.
Oh yeah, that was the fun part.
It actually kind of is fun. Once you sort of understand it, it's actually not that hard. So don't be stressed out about it.
That was sarcasm.
Oh, it's really not that hard, but it's a lot of information. So, but Bohr's theory is not completely just because we have this other model. His theory, though, the math that he did still is very relevant to our understanding of how the atom stays together. So it's not irrelevant. It's good information in how these electrons are moving. Just the quantum theory starts, instead of looking at just circular shapes of orbit around the nucleus, it starts to develop different shapes, and we will learn about that and how those electrons fit in there and how they jump and move around. it is important. I know it feels like a lot of information and like, why do I ever have to know this? And I guess if you don't become a chemist, you really don't have to know it, but there's a lot of cool jobs that involve chemistry. My hope is to expose you to some of those over this year, and maybe even do some kind of field trip to see some kind of cool chemistry job in action so that you'll be more motivated to learn about Bohr's model and the quantum model and all the stuff that you'll be learning in this next section. So, not a ton of math, right? Well, no, I take that back. There is math. Okay, so guys, when you go to work, I have another video. I'm not going to make it tonight. I wanted to go back and review something from Module 2, and I will have your quiz up for Module 2 hopefully by Tuesday, guys. It might be Wednesday because I work all day tomorrow, and I should have had it up sooner, but I really want to get that quiz up there. But I want to go back and review just a small section from Unit 2 that we kind of just, it's not even the section, we just kind of skipped over a concept. You should have read it, and you might understand it, but I want to make sure we address it. But when you go to work these problems, so you're going to see problems where they give you, here's a frequency, what's the wavelength, or what color would that light be then? So you have to figure out, well, what's the wavelength, to figure out what the color of the light is, things like that. But you're always going to go back to those equations. Frequency equals speed of light over wavelength, or lambda. You also have that energy equals Planck's constant times frequency. How's that, Delaney? Planck's constant. And gamma rays. The Incredible Hulk, he was made in Incredible Hulk by gamma rays, right? Did I get that right? Is it gamma rays? You don't know? You're the Marvel expert. It was gamma rays, right? It wasn't gamma rays?
No, it is ultraviolet light.
No, it wasn't ultraviolet. That's the sun. Gamma rays. I was right. Okay. When you go to do those, they will try to foul you up sometimes by giving you, not foul you up, but I'm trying to find an example. They might tell you that you just have to make sure all your units match. Make sure if something's in meters, like if speed of light is in meters and you're working with nanometers, you have to make sure they match. You can't just plug those all in there with one in meters and one in nanometers. You have to put the speed of light in nanometers. You have to put the wavelength in meters, something like that. That's where I even was getting messed up, and then I'm like, what did I do wrong? It was because of that. So look at your units. Make sure your units match before you start plugging everything in. The actual equations aren't that hard, but if you're not paying attention to that, that's where you're going to get messed up. What else can I tell you that would be helpful for this section as you're working things out? I think that's the biggest one, actually. It's really, really paying attention to your units. Work neatly. Show all your work. Even when you're doing your stuff in your workbook, show your work really neatly so I can see it. Excuse me, most of you have really good handwriting and it's easy to follow. So there's only 5 of you. I think you all have really good handwriting. So
Got out of it. Jack had all the
Jack Caldwell's not in this class, though. Jack, just teasing. Jack will never see this video. I love Jack. We can't all have perfect handwriting. What's that?
I'm
Mom,
sending
can you send me that video so I can learn from it?
So you can learn from it? Are you joking?
You honestly want to.
I think you're being
really helpful.
okay. Thank you, guys. I think you're just making fun of me. All right, that's the last of this section, guys. Like I said, I will put up another video. I'll try to make it tomorrow to review Unit 2, and then you'll have just part of Module 3 this week. So make sure you really understand what's going on with that. There's not a lot of work, so make sure you get them. And if you don't get them, do those extra practice problems. I am going to grade your stuff. Oh, no. I guess you do have all week to do it, so I guess I can't grade it Wednesday. I'm going to send your moms, or you guys, we're working on the honor system here. If you give me an answer and you don't show me the work, then I know you didn't know how to do it, so you don't get credit for it. So you do have to show your work even if you have the answers. But I will send you pictures of the answer keys while I'm gone here so you can get things graded, and then I'll plug it in when I get back. Okay, I think that's enough for one night, and good luck and Godspeed. Have fun. Bye.